Hi, everybody. It's Professor Mitchell. We are finishing up Chapter 8 today by talking about testing a claim about a standard deviation or variance. So the key concept in this section is to present methods for conducting a formal hypothesis test of a claim made about a population standard deviation sigma or population variance sigma squared. The methods of this section use a distribution that we have not talked about before called the chi-square distribution. So the objective is to conduct a hypothesis test of a claim made about a population standard deviation sigma or population variance sigma squared. So remember, so far we've talked about how to test a claim about a population proportion and a population mean. So now we're doing population standard deviation or variance. All right, the notation we'll be using in this section, N is the size of the sample, S is the sample standard deviation, sigma is the population standard deviation, and then S squared is the sample variance, and sigma squared is the population variance. The requirements are that the sample is a simple random sample and the population has a normal distribution. So unlike, well, I'm thinking of the last section especially, when it said normal distribution or samples of at least size 30, the original population has to be normally distributed, period. Okay, so the test statistic for this kind of test is called chi-square. This symbol here is the Greek letter chi. And here is the formula, n minus 1 times s squared, so that's the sample variance, divided by the population variance. And they suggest that you round these to 3 decimal places. And we will talk about the p-value approach. To get the p-value, you can use technology, or you can use a new table, which is table A4. So I'll be showing that to you. Or you can use the critical value approach. All right, so we've talked a little bit in previous sections about the confidence interval method. And we said that it is not equivalent when you're testing a claim about a population proportion. In other words, it can give you a different conclusion. However, if you're testing a claim about a mean, it will always give you the same conclusion. Well, that's also true for testing a claim about a population standard deviation or variance. The confidence interval method is equivalent. It will always give you the same conclusion as a formal hypothesis test. Now, as I record this video, we did not cover the section in Chapter 7 about finding confidence intervals for a population standard deviation or variance, so I won't be using that approach in this section. All right, properties of the chi-square distribution. So this is what a chi-square distribution looks like. Notice it is not symmetric. All values of chi-square are non-negative. And for each different number of degrees of freedom, there is a different chi-square distribution. You can see some examples here. All right, and to find critical values, you can use table A4. So I will include a link to that table in the description of this video. If you're one of my students, you can find this table posted on Canvas or Blackboard, whichever learning management system you use. An important note, if using table A4 for finding critical values, in table A4, each critical value of chi-square in the body of the table corresponds to an area given in the top row of the table. And each area in that top row is a cumulative area to the right of the critical value. So we're going to have to be a little bit more careful using the chi-square table, again, because the chi-square distribution is not symmetric. All right, so here's an example. Listed below are the heights in centimeters for the simple random sample of female supermodels. Use a 0.01 significance level to test the claim that supermodels have heights with a standard deviation that is less than sigma equals 7.5 centimeters, which is the population standard deviation of heights of all women. Does it appear that heights of supermodels vary less than heights of women from the population? So here is the sample. Checking our requirements, the sample is a simple random sample. And they didn't come right out in the original problem and say that the distribution is normal, so they're assessing the normality here. And again, we didn't cover that section. So in your homework problems, it will likely say that the original population is normal. Okay, on this side, they're showing you that technology capable of conducting this test will typically display the p-value. StatCrunch can be used as described at the end of this section, and the result will be shown in the figure. So we have not talked yet about how to set up the hypotheses for this test. That's coming on the next slide. But they've gone ahead and pointed out that if you're using StatCrunch, the hypotheses have to talk about the variance instead of the standard deviation. So notice in this case, the null hypothesis will end up being sigma equals 7.5. That's equivalent to saying sigma squared equals 56.25 because that's 7.5 squared. Okay. So as far as the steps for the test go, step 1, the claim the standard deviation is less than 7.5 centimeters is expressed as sigma is less than 7.5. The opposite of that claim in step 2 is that sigma is greater than or equal to 7.5. So remember, whichever one of those two statements does not contain equality becomes the alternative hypothesis. So there's the alternative hypothesis. And then the null hypothesis gets an equal sign. So the null hypothesis is sigma equals 7.5. The significance level is alpha equals 0.01. And because the claim is made about sigma, we're going to use the chi-square distribution. So again, here is this StatCrunch display. I'm going to do it a little differently. Okay, because the p-value is less than the significance level alpha equals 0.01, we reject the null hypothesis. So in the StatCrunch display, you can see the p-value ends up being less than 0.0001. Very, very low. All right, so the interpretation is that there is sufficient evidence to support the claim that female supermodels have heights with a standard deviation that is less than 7.5 centimeters for the population of women. It appears that heights of supermodels do vary less than heights of women in the general population. And I think that kind of makes sense. Okay. Using the critical value method, and part of this you can also use for the p-value method. Steps 1 through 5 would be the same. In step 6, we're going to calculate the test statistic. Now, the first thing I need to show you is how did they come up with S equals 1.8439, because that was not given in the problem. Well, remember, they did give us the sample data. So in this situation, you can always calculate the sample standard deviation yourself. So I am going to jump over to Excel, where I have already typed in this data. And I'm going to go to the bottom, and I'm going to type equals. And I think you've seen me do this at least once before. The formula for sample standard deviation is STDEV.S, and then put a parenthesis, and then select all the data that you want the standard deviation for. And there is the 1.8439. If I make this column a little wider, it will give me more decimal places, but I think 1.8349 is probably good enough. Okay, so let's see. Oh, going back to where we were. Oh, there we go. Okay, so we know the sample size is 16, and now we know the sample standard deviation is 1.8439. You plug all that into the formula along with the hypothesized population standard deviation 7.5. And we get that the calculated test statistic chi-square is 0.907. Okay, so let me show you how they came up with this critical value. It is found from table A4, which is right here. So if you go down to 15 degrees of freedom, because the sample size is 16, and then we want to pick the correct column for area to the right of the critical value. So remember that the level of significance as 0.01. That means an area 0.01 to the left of the critical value, because this is a left tail test. And that means 0.99 area to the right. So if I go over to the second column, I find this 5.229 that they have in the picture. Okay. So the critical region would be all chi-square values that are less than or equal to 5.229. Our calculated value of chi-square is 0.907, which is definitely less than 5.229. So that's another way that we would figure out that we should reject the null hypothesis. Okay. I want to show you one more thing. I want to show you how I get the p-value. So I am going to go over to here, over to my browser, where I have already pulled up a Google page and typed in chi-square distribution calculator. The first result that comes up is my favorite website, StatTrek. So I'm going to click on that. Okay, so here is the chi-square calculator. So we have to fill in the degrees of freedom, which is 15. I've already done this once, right? And then we need to fill in exactly one of these boxes. If I was using the p-value approach, the only thing that I would know would be the calculated chi-square test statistic value. I think it's a little confusing that they say critical value here, because that's not exactly how we've been using that terminology. But so I'm going to type in 0.907. And in this box right here, it's going to give me the probability that chi-square would be less than or equal to that value. And it turns out that that value is very, very close to 0, right? It's practically impossible that that would happen just by chance in a world where the standard deviation really is 7.5. So we are looking at very, very strong evidence against the null hypothesis, all right? Because if, again, if the population standard deviation really was 7.5, there is practically 0 probability of getting a sample with a sample standard deviation this low, all right? Practically impossible. All right, so in step 7, we reject the null hypothesis. This is going back to the critical value method. Reject the null hypothesis because the test statistics chi-square equals 0.907 falls in the critical region. We conclude that there is sufficient evidence to support the claim that supermodels have heights with standard deviation less than 7.5 centimeters. Same conclusion that we got before. Okay, let's do one more example. The simple random sample of birth weights of 30 girls has a standard deviation of 829.5 hectograms. Use a 0.01 significance level to test the claim that the birth weights of girls have the same standard deviation as birth weights of boys, which is 660.2 hectograms. And I'm going to try something I haven't tried before. Because I just added this example at the last minute, I don't have it all typed out. I'm going to do it on my pad. So it'll be kind of like watching me do it on the whiteboard. So let me switch over to my pad. And I'm going to use the same 8 steps that we've been talking about. All right. So the first step is to identify the claim made in the original problem. All right, so the claim made in the original problem was that girls' birth weights have the same standard deviation as boys' birth weights. So the claim is that sigma, which is the population standard deviation of girls' weights, is the same as boys, which is 660.2. That is the original claim. In step 2, we write the opposite of the original claim, which would be sigma does not equal 660.2 hectograms. And then in step 3, we decide which of those is the alternative hypothesis. The alternative hypothesis is the one that does not have equality. So that is sigma does not equal 660.2. And then remember, in your book, the null hypothesis always has an equal sign. All right. So there's our first 3 steps. Fourth step, we select the significance level that's been selected for us. They told us to use a significance level 0.01. And then in step 5, we identify the test statistic. Because the claim in this problem is about a population standard deviation, that test statistic is chi-square. So we're going to use chi-square, which is n minus 1 times s squared divided by sigma squared. Okay. So those are the first 5 steps, and those first 5 steps are the same regardless of whether you use the p-value approach or the critical value approach. Okay. So now I have to make a decision. Am I going to use the p-value approach or the critical value approach? I am going to recommend that if you're doing a 2-tailed test, and this is a 2-tailed test because the alternative hypothesis has a not equal as opposed to a less than or greater than. For a 2-tailed test involving chi-square, I am going to strongly recommend that you use the critical value approach. Calculating p-value for this type of test is kind of complicated. And since we have a choice and they're going to give you the same conclusion, let's just go with the critical value approach. I'm pretty sure that the homework in this section is set up to allow you to do it either way. I hope I'm right about that. That was sort of the vibe that I was getting from the textbook. Okay, so the critical value approach goes like this. In step 6, you find the value of the test statistic. So using that same formula that we were just looking at, chi-square equals n minus 1 times s squared over sigma squared. Remember, the sample size is 30. The sample standard deviation for the girls' weights is 829.5. And the hypothesized population standard deviation is 660.2. All right, and when you crunch those numbers, you get 45.780. Okay, so that is our calculated value of chi-square. All right, so now we have to come up with our critical values. And I'm going to use table A4 for that, but first I want to draw you a picture of what the critical values represent. So a chi-square graph looks kind of like this. Remember, it's not symmetrical. The significance level is 0.01. So what that means we need to do, because this is a two-tailed test, we want to find two values of chi-square. One of them is going to cut off the bottom 0.005 area under the chi-square curve, and the other one is going to cut off the top 0.005 area under the chi-square curve. Okay. All right, so now I'm going to go over to table A4. Okay. So we are at 29 degrees of freedom. So I'm going to place that so that it's right on the bottom. Well, first of all, let me point this out. So up here, we have to select the area to the right of the critical value. We're looking for two critical values. Let's talk about the easier one first. This very last column is going to give me a chi-square value that cuts off the top 0.005. So at 29 degrees of freedom, that would be 52.336. I'm going to add that to my picture, and then you'll be able to see it in just a minute. The other value cuts off the bottom 0.005. So to make that be about an area to the right, instead of saying 0.005 to the left, we're going to say 0.995 to the right. So you do 1 minus 0.005, you get 0.995. So at 29 degrees of freedom, that critical value is 13.121. All right, so switching back to my tablet. All right, this is what our critical region looks like. Okay, so we have the lower area is bounded by 13.121. The upper area is bounded by 52.336. Our calculated test statistic, that's what I thought, was 45.780. So that falls in between. The shaded area is our critical region, also known as our rejection region. So if our calculated chi-square value had been down here or up here, I would have rejected my null hypothesis. But since it's not, this is going to be a fail to reject. Fail to reject. So let's see, are we on step 7? Yes, I believe we are. We are going to fail to reject the null hypothesis. And now we have to write our claim. Okay, so, and we need to, okay, so we're failing to reject the null hypothesis. The null hypothesis was that sigma equals 660.2. Okay. Since we are failing to reject that, we're going to say something like, You know what? I think I can type this. This will look a little nicer. There is not sufficient evidence to warrant rejection of the claim that the birth weights, oh, I'm sorry, you can't see this. Let me see, is there a way for me to fix this? Okay, sorry about that. There's not sufficient evidence to warrant rejection of the claim that the birth weights of girls have the same standard deviation as the birth weights of boys. Okay. Not sufficient evidence to warrant rejection of that claim. Okay. So we're not saying we've proven those two standard deviations are the same. We just haven't gathered evidence to say that they're not the same. Right? Believe me, I know it's you know it can drive you a little crazy with the double and triple negatives in the conclusions, but that's the way you have to do it, because we were looking for evidence against the null hypothesis. We were not trying to find evidence to support the null hypothesis. Okay, so that's how it works, and I hope that extra example is helpful.